just to show that this 2021-22 winter in Mumbai is unusually cold, and in fact yesterday there was a western disturbance that came straight down from the Middle East onto Mumbai and Pune areas and created a massive dust storm, which is very unusual. So I'm wearing fleece in Mumbai just to make that point. It's a La Nina winter. We expect to be cooler than normal, but this is really unusually cold. Okay, so looking again at our flux formulation from the ocean to the atmosphere in terms of short wave, long wave going out, back long wave back radiation coming back from the atmosphere into the ocean, sensible heat loss and latent heat loss. Let's jump directly to how we would worry about evaporation or latent heat loss. Typically, especially when you go back to the beginning, as we saw here in terms of modeling, there were simple models. Stommel, of course, was doing process models, and then once we got into numerical models of looking at just the ocean, wind-driven ocean circulation, where these heat flux exchanges were not a concern, like in Stommel's western boundary intensification model, or you have ocean models where you want to look at the temperature variations, salinity variations, ocean currents and so on. Then you need to find a way to represent the heat flux at the surface, and wind stresses are also to be prescribed from somewhere. There were ship-based products before called Hellerman-Rosenstein winds, then came the satellite winds, then came reanalysis winds or coupled model winds, and so on and so forth. So here we are looking at just the thermal exchanges first. So evaporation is dependent on ocean temperature and atmosphere temperature. So the that can be written as an approximation of evaporation at ocean temperature and atmosphere temperature being equilibrated, and atmospheric temperature plus the gradient of evaporation dependence on ocean temperature. So dE, you better think of latent heat, but doesn't matter because we are talking about heat flux here. Its dependence on ocean temperature. Obviously, warm parts of the ocean have higher evaporation than cold parts of the ocean, as you can imagine. Right, so atmospheric temperature determines how much humidity it can hold. So the relation is obviously on saturation humidity at ocean temperature and atmospheric temperature, specific humidity at atmospheric temperature. So d dt ocean with T ocean being equal to T atmosphere times the difference T ocean minus T atmosphere plus higher order terms. This is just a Taylor series expansion around the ocean temperature. So in this case, an approximation was proposed where latent heat flux is represented with an exchange coefficient, exponential term that depends on atmospheric temperature times a difference of the ocean and atmospheric temperatures divided by Ta squared with another coefficient here. So obviously these kind of complex formulations are derived from observations of humidity levels, ocean temperatures, atmosphere temperatures, estimated latent heat fluxes, and their dependence on ocean and atmosphere temperatures. So you can begin to imagine how, when you have a coupled model or forced ocean model, you need all these data, or the model needs to simulate all these things, translate it into latent heat, and take the energy from the ocean or put the energy back, and so on and so forth. Okay, so how do we do then the net heat flux? So this is called often the net heat flux. So this is essentially the net heat flux. We are not separating here the short wave, long wave, sensible and latent. We are taking a sum of those and estimated sums of net heat flux going into the ocean or coming out of the ocean are given here. So that's the net heat flux. And if you have a forced ocean experiment you want to do because your main goal is to understand what's happening in the ocean without worrying about the details of how the atmosphere and ocean are determining the heat flux together, you can make some simplifications. So here, flux from the ocean to the atmosphere at ocean temperature is again represented approximately as the flux at atmospheric temperature plus the gradient of the flux depending on the ocean temperature at fixed measured at ocean temperature being equal to atmospheric temperature times the delta T. It's a very simple Taylor series expansion as you learned before. So that's the F0, so F ocean, that is, let's say, the climatology of some sort, plus some exchange coefficient times T ocean minus T atmosphere. So this is looking almost like the sensible heat flux, except that it is the perturbation on top of a background. So if you have long-term means, so these are the long-term means, so you can do seasonal or sub-seasonal variability or interannual variability of heat flux on top of this by knowing ocean temperature variations at those time scales and atmospheric temperatures at those time scales, and a exchange coefficient D star. So here F0 is at temperature TA, obviously, and D star is the gradient or the variability of the ocean to atmosphere flux depending on the ocean temperature when the ocean temperature is held constant at atmospheric temperature or measured at that background. Okay, so Haney then proposed a further simplification because here this still comes down to estimating. You have to have this from long-term measurements. So he said we can forget all that and just represent the ocean to atmosphere flux as the coefficient times T ocean minus T ocean star, where the T ocean star is atmospheric temperature minus the same thing. So we're just writing it in a different way, but it simplifies what you give to the ocean in the ocean model. So this is called here as restoring temperature, which means every time the ocean temperature deviates from the long-term average, the average temperature and the exchange coefficients are used to relax it back. So this basically ends up becoming a restoring time scale. All it means is if you are not worried about the details and you are focused on certain specific processes you want to understand, then you can treat the ocean temperature as basically varying around a mean and relaxing back towards that long-term mean with some time scale based on the local ocean to atmosphere temperature. We can understand that here. Maybe I should stop this here and explain the part in the next podcast, but I hope you are getting a sense of how hard it is to do not only ocean model, not only coupled model, but even just the ocean model. So when you have coupled model, we talked about the resolution issues, the computational issues, and if you do a regional coupled model, you need boundary conditions and so on and so forth. When you do just forced ocean model, you do need boundary conditions where the ocean is being forced by the winds alone if you're only interested in wind-driven processes, and then you prescribe either a fixed basin or a fixed stratification and so on and so forth. But when you do more realistic ocean, you need heat exchange as well as wind stresses, and of course evaporation, which is part of the heat exchange as well. But it also has mass exchange because you're taking water out of the ocean and you have to precipitate somewhere. So all those things get us into having to prescribe the quantities based on primitive variables like temperature, salinity, air temperature, ocean temperature, but then you end up with parameters like exchange coefficient, wind dependence, the latent heat flux dependence on exponential terms through the Clausius-Clapeyron equation that we looked at, and so on and so forth. So we can look at now one example of a simple heat balance and then try to understand. But the other thing to remember is that the maps of heat flux we saw estimated from COAD's data set has errors in it. They are observationally estimated, but they have errors. So then you have to understand that if you force an ocean model with a flux that has errors, then when the model simulated temperatures are not consistent with observations, then it becomes challenging to understand whether those errors are due to just the prescribed fluxes or because the ocean model itself has some deficiencies. If the errors are larger than the errors due to fluxes, then you can begin to say the ocean model itself has errors. Then you have to figure out what sorts of errors it has, whether it's mixing error, representation of the top surface mix layer, exchanges with the interior. All kinds of details come into play when we do that. I'm saying this now because modeling is a great challenge, even when we have lots of information about the winds and the fluxes and so on. Okay, keep that in mind.